So here we go. Let's review just quickly from last time. Here's two expressions. We want to write something that reveals what it represents. Can you do that? Can you write out what something, write something that reveals what this means or what it represents? We should be able to. So, when you see this, what do you think? What is this? Someone said a sequence. A sequence? And what is a sequence? A list, ordered list. So we can rewrite it as its list. How do we know what the first thing on the list is? How do we know? What generates the list? Yeah. What's that? Yeah, so and specifically then how do I get that first? I equals 1, right? So I really should have kind of put this here. That specifies exactly where I starts, but for our purposes, I is like which number in the list is it? So that would mean start at I equals 1. And what do we get for the first one? Everyone says together? 1/3, and then? 1/9. And we just keep going on like that. So this, when you see that thing on the left, you immediately think this, right? You think this, what I wrote. 1/3, 1/9, 1/27, the list, an ordered list. And then we have a special name for this kind of ordered list. Remember what that was from Friday? It's a geometric sequence, right? So this is geometric. Geometric has the form r to the I. And what happens generally in a geometric sequence? What's happening here? What's going on in a geometric sequence as we go from one term to the next? It's like repeated what? Repeated multiplication. I just keep multiplying by this r number, right? In this case, r is 1/3. So as I go from one number in the list to the next, I just keep multiplying by the r to get the next one. Just take the previous one, take the current one, multiply by r, you get the next one. So you just have repeated multiplication of r. And when does this converge? Does this converge? To what? Yeah, it's going to converge to 0. These are going to get really small. This is like on an old school calculator. If you like hit 1/3 and then go times. What's going to happen? The number's going to keep getting smaller and smaller until eventually it's just going to show 0. You can't show a number that small, and you just keep hitting times, and it's just eventually going to show 0. So this converges to 0 when r is between, so it's when r is like a fraction, right? When r is some fraction of 1, it can be negative too. As long as r is a fraction, you keep taking a slice of what you had before, and you just eventually that's going to get very, very small. As long as it's a fraction, right? As long as it's like something between -1 and 1, then the sequence goes to 0. Okay, what about this one? What's the first one in this list? 1. 1 over cube root of 2. 1 over cube root of 3. Is this geometric? Not geometric. Geometric is where you have some constant number to the I. This is P sequence. P sequence. 1 over I to the P. So somehow you got to memorize or file away in your brain the difference between these two until you're really confident and you can identify them quickly and without getting confused between these two. So when does a P sequence converge? Do you remember what we said? We kind of proved it. When P is greater than 0. As long as P is positive, this thing will get large eventually. That will get big. And if the denominator is getting bigger and bigger and bigger without bound, then the reciprocal will approach 0, converges to 0 when P is greater than 0. So the geometric and the P sequences if they converge, it'll always be to 0, but other sequences don't have to converge to 0. They can converge to any real number, okay? But these particular ones, they either diverge or they converge to 0. And what does convergence mean? It means getting closer and closer, infinitely close to one particular value. So that kind of in the end, when you get out to the billionth, the trillionth, the zillionth term, it's essentially the same number over and over again. So close that it's basically you're just at the same number, and that's called the limit of the sequence. But if it does anything else besides hone in on one particular number, we say that sequence diverges. All right, that's all review. Questions? Yes, sir.
What's the general form of a P sequence if geometric is R to the I?
It would be, so this is where P equals 1/3. So you tell me. So this particular one is P equals 1/3. 1 over I to the P. That's it. That's the general form of a P sequence. So P is the constant, right? But I is the index, the 1, 2, 3, 4. Other questions? Okay, so that's a little review. Here's another tool for our toolbox for determining if a sequence converges. So Hopital's rule is for functions, and we said last time that we can for every sequence there's a corresponding function that's kind of the same as the sequence, but for continuous values x. So here's the Hopital's rule for analyzing some certain functions. So if a function has the form f of x over g of x, if you let x get really big, if that function becomes like infinity over infinity or 0 over 0, then this rule applies. And what you can do is you can take the derivative of the numerator and the derivative of the denominator, and that new ratio will have the same limit as the one you're analyzing. So if I have a function h of x, and it's 3x plus 1, sorry, same thing this morning. So if I have a sequence, 3I plus 1 over e to the I. So I can look at the corresponding function, 3x plus 1 over e to the x. And whatever this does as x gets big is going to be the same thing that our sequence does as x gets big, right? So the only difference between these two is this is only for I equals 1, 2, 3. Whereas this is x is a member of the real numbers, right? Continuous. But whatever this does in the long run, whatever h does in the long run, so will that sequence do in the long run, okay? So this thing goes to what? Gets big as, or both the numerator and the denominator get big as x gets big. So this is a candidate for Hopital's rule, because if you let x get large, the numerator gets large, and the denominator gets large. That's one of our indeterminate forms. So sometimes this is a finite value. Sometimes it's 0. Sometimes it's infinity. Sometimes it doesn't converge. So that's why we call that an indeterminate form. So Hopital's rule says, make a new function. Now this is not h prime, right? Because h prime would be the quotient rule. It's not the quotient rule, right? Quotient rule is more complicated. This is Hopital's rule that says take the derivative of the top and the derivative of the bottom. And see what that does. What does that do? 3 over e to the x. That's going to be 0, right? E to the x gets big, fast. 3, it's just 3, so this is going to be a big, big denominator. That will go to 0. So therefore, by Hopital's rule, therefore this function goes to 0 because this ratio of its derivatives goes to 0. That's what Hopital's rule says. And if this goes to 0, then our sequence goes to 0. Okay, does it make sense? Hopital's rule. In the case where you have infinity over infinity, or 0 over 0, you can take the derivative of the top, derivative of the bottom, and the new ratio, you can evaluate that limit. And that limit will have the same limit as your original limit. Okay, so let's just quickly here is a toolbox, right? This is kind of our toolbox so far. So the first thing you want to always do is look for your geometric and p sequences. Identify that if you have one of those, and then we know when those converge and when those diverge. All right, limit function techniques. So on Friday, I talked about rational functions. So if you have a polynomial, one polynomial divided by another, it's where you compare the degrees of the numerator and the denominator, and then we've got some different cases for that. We did that Friday. And then we just did Hopital's rule. So those are function limit techniques. All right, another technique is just to list out the first several terms. Sometimes that's enough to see exactly what's going to happen, especially for some that diverge, right? So you can see just by listing out 4 or 5 terms, it's going to diverge. And then there's going to be some algebra and pre-calc and deductive reasoning in these. So all these things come into play, sometimes in combination. Just takes experience. So the problems are kind of they're not pigeonholed. They're kind of varied. And you have to kind of gain some experience knowing which technique to use, or sometimes more than one technique. So any questions on that? Now you're going to get a chance 5 or 10 minutes to work on some examples. Okay, and here they are. So this will be in the video if you didn't finish writing it down. All right, so for these, what we want to do, we want to write out, so let's just make it the first 2 terms, so for time's sake, instead of 3. So write out the first 2 terms of each sequence, and then does the sequence converge or diverge? State reasons, and then if it converges, determine the limiting value. So let's just work on these for about 5 or 7 minutes. Work together. Don't get stuck, spinning your wheels. Either move on or talk to somebody, but everyone's either making progress or getting help. Okay. Let's regroup here. Okay, so first one. What is going on here? What kind of sequence is that? Okay, we can do better than that. -4 to the I is? I haven't heard it yet. -4 to the I. Geometric. Gotta be on the lookout. Geometric and p sequences. R to the I. Any constant value to the I is geometric. Okay, and then 1 over I to the p is a p sequence. So, does it converge or diverge? So you can see it diverges by looking at the sequence, but then also we can just go back to our geometric sequence. Why does it diverge? Because? Yeah, R equals -4, which means it's not between -1. So this diverges because R is -4. But you can, this one you can just see by listing out the terms. But you should also be able to recognize that as a geometric sequence that does not fall between negative, R does not fall between -1 and 1. Okay, how about this one? Converges or diverges? Okay, so the way we can do this one is we can first focus on the parentheses, what's inside the parentheses. And this is what? This is one of our rational functions. And we've got the degree of the numerator is, and the degree of the denominator is the same, right? So that right there will approach 1/3, right? So when the degrees are the same, it's the ratio of the leading coefficients. Think about this. If you have 1 billion squared divided by 3 times 1 billion squared, what is that? That's essentially 1/3, right? The billion, these, when things get really big, that will just cancel out. And you'll just have the ratio of the leading coefficients as so that thing in the parentheses goes to 1/3 as I gets big, and therefore, what will this sequence do? If that thing approaches 1/3 and that's the sine of all those terms, then it'll approach sine of 1/3. So this converges to sine of 1/3 by looking at that as a rational function, I squared over 3i squared minus 7. And you could also use Hopital's rule on this. If you do Hopital's rule, you get 2i over 6i, which is 1/3, right? The 7 minus 7 goes away, so 2i over 6i is 1/3. So you get it by Hopital's rule as well. Then the sine of that. Okay, next one. Okay, p sequence, right? P sequence. 1/i to the, what is the value of p here? Since p is 1/2, sequence converges. So you can say, since p is 1/2, which is less than, what, greater than 0. Sequence converges. Okay, next one. So it's just forever going to skip around between 1, 0, and -1. Converges or diverges? A sequence converges if the terms hone in at a particular value, get super close to one value until it's essentially that value forever. Right? That's what we want. This does not do that. This keeps jumping around. So anything but sequence converging means it diverges. Next one. So notice again, we have another rational function under the square root. We can focus on the rational function. What will that do? I to the 4th over I squared. If we have the degree of the numerator is greater than the degree of the denominator, this will get large. This will get as big as you want. Go to infinity, if there's such a thing. So therefore, what about the square root of all those terms? Still, so I mean, so you still, it gets as big as you want. It just does it slower than the fraction. But this will get as big as you want it to get. Just pick an I number big enough, and you can get that square root to be as any number, any size number you want, just by picking I to be a big enough number. Diverges. By rational function limit. Okay. Degree of n greater than degree of d. Next one. What do we got there? P sequence. P sequence, what's the value of P in this one? P equals 4, because this is the same as 1 over I to the 4th. So P equals 4, that's greater than 0. And you can see what's happening here. Very quickly, it's getting small, right? So if the denominator gets big, the whole fraction, the whole fraction gets small. So this P sequence converges to 0, right? Converges to 0. How about this one? What do you got here? pi to the I over 3 to the I is the same as pi over 3 to the I. What do we got? What is it? Geometric. Always look for geometric and p sequences first. This is a geometric sequence. What's the value of r? Pi over 3, which is greater than 1. Therefore, diverges. Pi is a little bit greater than 3, so that thing's a little bit bigger than 1. So now we're multiplying by a number over and over again that's a little bigger than 1. Well, that's just going to get as, again, we'll get as big as you want it to get, just with a large enough value of I. So this diverges. Okay, now I have over 3 to the I plus 1. Same one. What about that? Converges? So what is 3 to the I plus 1? Right, so this tells you how many times to multiply 3 together. So it's one more time than 3 to the I. So how could I change 3 to the I to get 3 to the I plus 1? Times 3, right? This should make sense. The exponent tells you how many times to multiply that base together. So 3 to the I plus 1 is the same as 3 to the I, which is 1 less time, times 3. So now those are the same. So what do I have? I have pi. I really have pi over 3, just like the one above, to the I, and then times 1/3. Do you see it? Does it make sense? Converge or diverge? So this diverged, right? This got really, really big. Now we're just taking 1/3 of all those values. Is that going to converge? Nope, it's still going to get big, just 1/3 as fast as this one gets big. So just multiplying, just having a 1/3 on this thing doesn't help it converge. It just makes it diverge more slowly, because all the numbers are 1/3 of what they were in this list. All these numbers are 1/3 as much as the ones in this list. If this one gets really, really large, then that will get really, really large too, just 1/3 as fast. Diverges. This is another geometric sequence. Basically for the same reason as this. All this stuff right here. They're basically the same problem. G and H are essentially the same problem, except for this has a 1/3 tacked on it. That doesn't help it converge. It just makes it diverge more slowly. Okay, questions on any of these examples? Okay, we have time for the last part. Any questions? All right, so the next part is... No, we don't have time for that. We have time for this. Factorials. Factorials. So factorial is symbolized this way. 4 exclamation points. And it does not mean 4. Right? Yes, 4. No, it means this. It means start with the number and then multiply by the number 1 less, and then keep doing that until you reach 1. You always stop when you reach 1. So 4 factorial is 4 times 3 times 2 times 1, and that's 24. So what's the use of this? This is one use of this is it's like how many ways could you assign 4 toys to 4 different babies, as an example, right? So how many ways could you hand out 4 toys to 4 different toys to 4 different babies? It would be 24 ways, because you got 4 choices for the first baby, and then 3 choices for the second baby, and then etc. So it'd be 24 ways you could do that. So that's one example of a use of factorial. All right, so 0 factorial by definition is 1. We won't get, that's a philosophical argument. Discussion, we don't have time for it, but just know that whenever you have 0 factorial, it is not 0, but it is 1. Okay? So what's 6 factorial? What is 6 factorial? We start with the number, start with 6, and you multiply down, and you always multiply down until you get to 1. 6 times 5 times 4 times 3 times 2 times 1. And that's 720. 6 factorial is 720. Yes, sir.
If we're writing this in like summation notation, would we have to do that for each term?
If there's factorial in a sum, yeah, then it applies to every term of the sum. Is that what you mean? These are not sums. These are products.
So if you had like say 2 factorial, and then the next one was 3 factorial, you'd have to do 2 times 1, and then for the next, you'd have to do 3 times 2 times 1. You'd have to
I
write
think
out
so. Are
instead
you
of
saying
putting 3
I factorial? Is that what you're saying?
Yes.
I factorial? Yeah, then you have 1 factorial plus, 2 factorial plus, 3 factorial plus, 4
But
factorial.
like say if you got to like the 5th term, would you have to do 5, or could you just put 5 and then the factorial, like the exclamation point? Would
Well,
you
it
have
means
to
the
write
same
out-
thing. They mean this 5 factorial means 5 times 4 times 3 times 2 times 1. They mean the same thing. So they both are the same thing.
Okay.
So whenever you write 5 factorial, it means start with 5, multiply down to 1. So if you don't need to write it out, you don't need to write it out. Come on, here we go. All right, so then what would 28 factorial over 25 factorial be? Well, let's take a look. So I don't need to write. All I have to do is just get the pattern going and then do this. But then what do you notice about 28 factorial? Do you see that 28 factorial has 25 factorial in it? Every factorial has, as a factor, all the previous factorials. So 28 factorial includes 27 factorial as a factor, 26 factorial as a factor. That's why it's called factorial, because you keep adding to the factors. So this 28 factorial has a tail in it that's 25 factorial. If we're going to divide by 25 factorial, then it goes away. That's all 1. Therefore, what is this? All it is 28 times 27 times 26. Because the 25 factorials go away.